Welcome to EDU World Space.
This is chapter 21, problem number 32. We're given the net electric field at a point midway between the two charges. These charges have equal magnitude but opposite signs. So let's put the positive Q here, and then negative Q. R also is given. The separation distance between these two charges is 16 centimeters. So, all right. The electric field at midpoint, the strength is given to us as 586 newtons per coulomb. And as you can see, this R equals 16 centimeters, the distance from one to the other. Now we're asked what Q is and what negative Q is. All right. Now, in order to answer this question, let's, look at this point that we're given, a midpoint between these two charges. So there are two electric fields contributing, right, adding up at this midpoint. One is emanating from the positive charge, the other one is emanating from the negative charge. So let's look at the direction of the electric field emanating from the positive charge. For a positive charge, right, the electric field generated by it is always away from it. So this would be the direction of the electric field for the positive charge. Let's look at the negative charge. For the negative charge, the electric field is always towards the negative charge. So then at this point, the electric field is pointing also the negative charge. So as you can see, these two electric fields, let me write down a positive Q plus a negative Q in this case, since they're all in the same direction, which means the total electric field is also in the positive x direction, in the direction of E negative Q and EQ, right? So we can simply add the magnitudes. Don't worry about the vectorial addition now. So EQ plus E negative Q equals to this total electric field then, right? So let's see what EQ is, the magnitude. KQ over the distance from the charge to the point that we're interested in. So that would not be R, but it would be R over 2 squared, right? This is an important point. We're not using the entire R. We're only using in our equation is the electric field at this point generated by positive Q. So this is the distance that we're using, which corresponds to R over 2. Plus, for the negative charge, again, we're finding the magnitude, so we're going to only take the absolute value of this charge. Again, the same story, R over 2 squared. If we add them up, it's going to be equal to the total electric field. Now, let me continue here. K over R squared over 4, then another KQ R squared over 4 equals to this electric field, right? So what we can do, I'm going to continue it here. The E equals to then K4Q over R squared, and another term comes from the second, right? So you might as well multiply this term by 2. This is going to give us the electric field. Then let's put this 2 in there. K8Q over R squared is going to give us the strength of the electric field. However, we want to solve this equation. E equals K8Q over R squared for Q, right? So then we're going to multiply both sides by R squared divided by 8K. We're going to do the same for the left-hand side. These are going to cancel out. On the right-hand side, we only have Q. So E R squared over 8K is going to give us our Q. 586 newtons per coulomb. R squared 16 times 10 to the power negative 2 meters, right? Don't forget to convert centimeters into meters. Squared divided by 8 times 8.99 times 10 to the power of 9 Newton meters squared per coulomb squared. So from here, we're going to find the positive charge to be 2.09 times 10 to the power of negative 10 coulombs. Then our negative Q has to be the negative of it, right?